Hello everyone. So in this video, we are going to do some live Matlab coding, and then we're going to implement convolution sum. And the way we're going to do that is we're going to replicate the same example which we did during the lecture, but this time we're going to do this in Matlab. Let me first walk you through a brief recap of the derivation of the convolution sum. First, we said that any signal like this can be expressed as a linear combination of delta signals. What I mean by that, let's say if you have a discrete signal x of n, for example, which looks like this, then you can write this signal as a sum of these three signals, signal 1, signal 2, and signal 3. Note that each of these signals here are just delta functions but shifted and scaled. The scaling factor should be equal to, if you shift by 1, the scaling factor should be x of 1. If you shift by 2, the scaling factor will be x of 2. Okay, so but I hope this was pretty obvious on how you can represent this signal as a sum of these three signals here. The point being, the original signal x of n is now a linear combination of a bunch of delta functions. So then we're going to use the properties of linear systems, saying if the input is a linear combination of some delta functions, then the output or of any functions, in fact, then the output will be the same linear combinations, but this time the linear combinations of the outputs of these original functions. So for example, here x of n is a linear combination of x of delta of n minus k, where x of k were the scaling, were the coefficients in the linear combination, right? So if you fix a k, this is just a number. So for each a, you have a number, and then you have another signal. So for each k, you have a signal and a number. So this is like a linear combination of all these deltas. And then let's say for each delta, uh, T of delta n minus k will be the output for that signal. Then the output of the entire signal, or the output of the entire linear combination, would be the linear combination of the outputs. So let's say the output of delta n minus k, the output of delta n minus k is yn minus k. Then the output of x of n would be this linear combination here, right? And in general, uh, when this y, this basically y here is substituting the impulse response, because if you put k equal to 0, delta n is the impulse, then y of n will be the impulse response. And then we usually use the word, the letter h to represent impulse response. So therefore we got our convolution sum, where the output of the signal is a linear combination of shifted impulse responses, scaled and shifted impulse responses, right? So we took a example system. So this was again our original signal, and we look at an example discrete system where the impulse response is given like this. So if the input is 1, the output would be 1 1 1. Okay, so and then all right, so we said the x of n was sum of these three signals, signal 1, signal 2, signal 3. And then in order to compute the output of the sum of all these three signals, you compute the sum for each of this signal, or you compute the output for each of this signal. And then once you get the output for each of the signal, you sum all of them up, and then you get a final signal which looks like this here, which is the output of the output for the signal x of n. Okay, so that's basically demonstrating the convolution sum, right? So for each impulse or for each delta signal, you have an output. And when the in so for each delta signal, you have an output. The input is a linear combination of bunch of delta signals. So you take the output of this bunch of delta signals, and then in order to compute the output of the actual x of n, you sum all these, outputs of these impulses, and then you get the actual output. And mathematically, that's what this represents here. So now let's look at implementing this in Matlab. So the first thing I want to do is just clear everything so the workspace is clean, and see CLF if there's a figure. Okay, and then let's do some initial setup here. So I'm gonna do set 0. I like my figures to be docked, so I will just say by default everything should be docked. So figure window style to be docked. Now if I open a figure, it will open as if it's docked. So first I want to create this signal x of n, where whose value says x of 0 is 2, 1 is x of 1 is 1, x of 2 is 0.5. Okay, so let me set my discrete indices going from -1 to 10. And let's see, so first I will create a vector full of zeros with length of n as columns and length of n as rows, one column. And then I can say x of, note that the first value should be for -1, so that should be 0, right? So then x of 2 through 4, 2, 3, 4, there are three values, and these values should be 0 0.2, sorry, so 2, 1, and 0.5. And then I want to make a column vector, so I'll do that. Then let's see, if I try to print x, what will it print? So this is -1, x of 0 is 2, 1 is 1, x of 2 is 0.5. I can also plot this. If I want to do a stem plot, I can say, okay, index on the x-axis, the actual signal values on the y-axis. And let's say if I plot this, then I get this. So 0 is 2, for 1 is 1, 2 is 0.5, and 0 is everywhere else. Next, let's create the impulse response. So I will say h is equal to also the same thing. So first create a bunch of zeros, and then I'm going to modify that. So h from 2 through 4 will be equal to 1, 1, 1, which was our impulse response. Look at our impulse response. If the input is just an impulse, the output would be 1, 1, 1, and that's our impulse right there. Okay. So let's plot both x and h and see them simultaneously. So let's see. Um, I want to create subplot. Maybe so. I want to create some few more subplots later. So I'll say 3 rows, 2 columns of subplots. Then let's pick the first subplot, and then I'm going to plot stem nx in the first subplot, and let's just and then select the second next subplot. So 3, 2, 3. So this will be just below the above subplot, and then I can say stem. Let's say this time I want to plot n, h, and then if I run this, so that's how it will look like. So this is I can also draw some more uh, context on this. So this would be x of n, okay, and the title for this should be h of n. If I run this, I have x of n here, h of n here. Next, I want to make the plots look a little bit more prettier. So that means I need some more gap on the top. So I can say while going from 0 to, let's say, 4. If I run this, I get something like that. And then I can do the same thing for this other subplot. And then if I run this, I get something like that. Okay, so that's my x of n. That's my impulse response. So what I want to do next is calculate all these three signals, right? So the output of the first impulse response, and the output of the impulse response shifted by 1, and the output of the impulse response shifted by 2. So I want to first calculate these three outputs and then plot them, and then take the sum of all of them, and then plot them. So this first signal will be x of 0 times h of n. This second signal would be x of 1 times h of n minus 1, and so on. So coming back to Matlab, so my first signal will be x of 0. So x of 0, note that it will be, since my indices are starting from -1, that means I have to do x of 2, right? Because in Matlab indices start from 1, and then the first x of 1 so corresponds to n equal to minus 1, x of 2 corresponds to n equal to 0. So this should be x of 2. So in when you write this, basically this x of 2 number corresponds to actual signal x of 0. So this times I just do my signal h, right? This would be my y1. Okay, so now let's plot this and see how this looks like. So since I'm going to be repeating these plots multiple times, I'm going to write a small function here. So I can say function my plot. So if I want to plot the signal, right? So that I'll take the indices first, and then I'll take the signal. So I'll also take another parameter saying, okay, which plot number, where I want to plot it, and what should the title be. Okay, and that's a function. And let's see, so inside here I go to subplot. Let's do 4 rows. Okay, 4 rows and 2 columns, and then the plot number. So this is the plot I'm selecting, and then I say stem signal, and then I can say title is 0, sorry, this would be title just be t, so you have to give the title as a parameter. And then I can also set the y limits from 0 to 4. So now let's plot my signal. So this will be my plot. N comma y1 I want to plot. So for number, so I want to plot it right here. So this will be first plot, second plot. So I give number 2. And then for title, I say y1 of n. Okay, and then if I plot this, I have my first signal. So you can see this is impulse response is scaled by 2, and it is not shifted. So this is h 2 times h of 0 basically. Sorry, this is 2 times h of n minus 0. So let me write that here for clarity. So this would be x of 0 times h of n. So next I want to create x of 1 times h of n minus 1. Okay, so let's do that. Then let's call this y2. So this would be, so x of 1, we can pick it at x in the third value on the array, times, so h of n minus 1, I want to shift h to the right. So if you notice h, there are a lot of zeros on the right. So even if I do a circular shift, so it will be basically be, it will be adding zeros to the left. So it will be as if I'm just shifting h of n to the right. So even if I do a circular shift, so I can do circ shift. So this would be circ shift of h comma shift by 1. Okay, and then let's plot this. So I'll do my plot n comma y2. So I want to plot it right here. So this will be 1 2 3 fourth plot, number 4, and then I say y2 of n as the title. Let's run this. That will be, as you can see, so it's scaled by 1, so it's exactly what it is. Let me, so to make uh, the plots a little bit more prettier, I think, well, that's fine, the limits are fine. Okay, so this is the impulse response shifted by 1 and scaled by 1, right? So this is basically x of 1, which is value is 1, and then I'm shifting my impulse response by 1 to the right, and then that is my signal right there. So that's this x of 1 times h of n minus 1. So the next thing I want to compute is x of 2, x of 2 times h of n minus 2. So I can compute this as y3 is equal to x of 4 times circ shift h comma 2, and then I can do my plot n comma y3. So I want to plot it right here, so I pick the sixth plot, and then I say y3 of n and run this. So I have this time scale by 0.5. So I have all the 3 signals I want it, right? So input of the first, impulse, output of the first impulse, output of the second impulse, output of the third impulse. So my actual output to the signal x of n should be the sum of all these three signals. Okay, so let's calculate the actual output. So that should be equal to y1 plus y2 plus y3. So if you notice, this particular sum here, y1 plus y2 plus y3, is exactly this sum here. Okay, so not even though this is k equal to minus infinity to infinity, x values are non-zero only for k equal to 0, 1, 2. So this basically, this sum boils down to sum of three signals because x of k is 0 everywhere else. So that is the sum y equal to y1 plus y2 plus y3. So next I want to plot this signal y and confirm if this matches with our calculations in our lecture. So I can say my plot, uh, n y, and then I want to plot it right here. So I want to pick number 8 and then plot y of n, and let's run this. So this is how it looks like. Okay, so it says 2, 3, 3.5, 1.5, 0.5. So let's see if is that what we calculated in the lecture. 2, 3, 3.5, 1.5, 0.5. Okay, so it's the same signal which we calculated by hand, but this time we did it in Matlab. So next, let's verify our calc. So right, this at this point we did it two ways, like more by hand and by using Matlab, where we computed individual signals and take the sum. So we just verified if our calculations are consistent, but we also want to maybe match this with some external third-party calculations and see if it matches with that too. So Matlab has a function called convolution. So we're gonna see if let's do this using Matlab's inbuilt function and see if we get the same results. So Matlab has a function called conv, which calculates the convolution, basically convolution of two signals. So conv of a comma b convolves the vector c and b. The resulting vector is length of a plus length of b minus 1. Okay, so y is, and then it's a little bit more complicated, but for our purposes, let's say length of a plus length of b minus 1. So why is that? So let's see, if you go back to our lecture here, right? So we are shifting these signals and adding up all these signals, right? So the final most signal, let's say if our signal was length 3, right? So in this case, it is 0, 1, 2. So it's basically three values. And so the final output of the impulse would be, you take the impulse response and shift it by 3, or right? So, or maybe how to say, you put it basically at the third value here. Okay, so the final impulse response starts at the end of the first signal, or the length of this, or let's say the output of the final impulse response starts where the signal ends, right? So if the signal length is, let's say, capital N, so this 2 will be capital N, and then you will add the rest of the values in the impulse response. So if the impulse response is length capital M, so the total length will be capital N plus capital M minus 1, because so this is overlapping with this, so you're just adding the rest. Okay, so that's why the length is length of A plus length of B minus 1. So this is how you use it. So I'm going to just use it to calculate, let's say, yc is equal to, let's say, convolve my input x uh, with my impulse response h. Okay, so it will be of of length greater than h, right? So when I'm plotting, then I'll just select the specific part of the signal I want to plot. My plot. So this will be n comma yc of 1 to length of n, comma, then I want to plot it, let's see, I want to plot it right here. So I'll pick the 7th plot, and then I want to title as Matlab convolution. Okay, so let's run this. Okay, so this is the Matlab output version, and this is our version. You can see they're exactly the same. Okay, so okay, so in this exercise we did, we saw how to do plotting, we saw how to do like uh, sums of different signals, um, and we basically demonstrated how, where that convolution, the formula for the convolution sum comes from, and we basically implemented that convolution sum in MATLAB.